We're going to go on. We're going to start off back with aromatic compounds. We're going to get real quick into talking about electrophilic aromatic substitution again. But I discovered that I have to go back into the aromatic chapter because I did forget one important reaction, and that's the Birch reduction. Birch reduction involves taking a benzene ring and reacting it in conditions similar to the dissolving metal reaction. And if you remember, using dissolving metal with an alkyne reduces the alkyne to an alkene. It's going to reduce a benzene ring as well, but it's going to do it in a particular way, and there's going to be some interesting nuances that are associated with that. So let's get right into that, and let's think about Birch reduction, and then we'll get right back into electrophilic aromatic substitution reaction. So at the in its simplest format, Birch reduction takes a benzene ring, reacts it in conditions similar to the dissolving metal reaction. Just going to add some methanol in here as well. And I can reduce the benzene ring, but only one of the double bonds. So I reduce it to an alkene, a diene, and it's not even conjugated, they're isolated. And so I want you to think about what this looks like. Notice that the two double bonds are directly across from each other. That's going to be a requirement for a Birch reduction. Now, it turns out that if I do a Birch reduction with an alkyl group, I notice something different than if I do a Birch reduction with an electron withdrawing group. So remember, alkyl groups are electron donating through hyperconjugation. That's why carbocations are stabilized with the increasing number of alkyl groups. But what I notice when I do Birch reduction is that I get different outcomes. When I have the electron donating group, the position next to the electron donating group is not reduced. When I have an electron withdrawing group, and I just cannot make this the way that I want it. When I have an electron withdrawing group, the position next to the group is reduced. So again, let's focus real quick. This carbon was not reduced, this carbon was reduced. And so this is a situation that comes out and you have to take into account. So this one is electron withdrawing, so or electron donating. Electron donating groups do not get reduced. Really, I mean the carbon next to that. Electron withdrawing groups do get reduced. And again, I mean the carbons next to the electron withdrawing group or the electron donating group, respectively. So what that means is that you have to have those things in mind when you're doing a problem that involves a Birch reduction. So let's do a quick example where I have both electron donating groups and electron withdrawing groups. So let's take a look at how this works. Okay, so there's going to be a product, and the product will have three different considerations to make. The first consideration is that this carbon gets reduced. This carbon does not get reduced. So that leads me then to a couple of possibilities. If this carbon does not get reduced, then that means the double bond can be there. I'm going to change it up to brown. It can be there, or it can be here. Because in either of those situations, those double bond, that carbon would not be reduced. If it were the situation in brown, then the last piece to remember is that the double bonds are across from each other. And so that means for the brown situation, it would be there. And for the blue situation, it would be there. And so all three of these possibilities have to kind of get into consideration all at once. The ethyl group is not electron withdrawing. The ethyl group is electron donating through hyperconjugation. The blue situation, all I'm saying with, okay, so let me just back up a second. The electron withdrawing group is the carboxylic acid. The electron donating group is the alkyl group. Electron donating groups put electrons into the ring. Electron withdrawing groups pull electrons out of the ring. The alkyl group is electron donating through hyperconjugation. We've explained this when it comes to the stability of carbocations. Electron withdrawing groups pull electrons out of the ring, and it's through resonance. So you can just show a resonance structure of the carbonyl group acting as an electron sink, pulling electron density away from the ring. So what am I showing with the blue and the brown again? What I'm showing with that starts here. If I'm telling you that the electron donating group does not get reduced, then that means I have two possibilities for where the so let's look right back up here in the corner. Electron donating groups do not get reduced. So just change your mind on that one. All right, so if the electron donating group doesn't get reduced, then the blue and the brown describe two different possibilities. The possibilities are where the double bonds are. We know that there has to be a double bond connected to that carbon. Okay, if we know that, then that means it can either be the blue one or it can be the brown one. Then we know where the other bond goes because the double bonds are across from each other in a Birch reduction. But all three things have to be consistent. The electron donating group does not get reduced. The electron withdrawing group does get reduced, and the double bonds are across from each other. So there's only one situation where all three of those are in agreement with each other. So we do not want a double bond at that location. So that means we're stuck with that as the product. So that's it with Birch reduction. It's quite simply take an aromatic ring and reduce one of the double bonds. You end up with double bonds directly across from each other. Different things happen about those double bonds and their locations based on what type of group it is. Electron donating groups don't get reduced. Electron withdrawing groups do get reduced. You have to bring all of those things into consideration when you're looking at a reaction that involves a species that has both types of groups on it. You may come to the conclusion that there's no reaction because you can't put all of those things, all of those pieces together. But you do have to bring all of those pieces to the table when you're considering Birch reduction. So I'm going to pause right there just for a second to see if anybody else has any other questions. And I want to then move back into electrophilic aromatic substitution. So that fills in the gap that I missed from that last chapter. Anybody? Pause in just a beat. Okay. All right, so let's kind of think about where we were last time. Last time we did bromination. And we started off the bromination mechanism by considering the reaction of bromine with iron tribromide, FeBr3. We showed how these guys form the species that ultimately acts as the electrophile for the electrophilic aromatic substitution reaction. This is negative and this is positive. So this was the electrophile. And if we think about it, then the basic reaction involves benzene reacting with an electrophile and having the electrons in the benzene ring form a bond with the electrophile. Then we get into this intermediate, and the intermediate was resonance stabilized over at least 3 structures. We called this thing the sigma complex. Now I'm going to finish it out here. And then the last step involves some sort of base. And that base reforms the aromaticity. And so at the end of the day, this is the basic reaction mechanism for the electrophilic aromatic substitution reaction. And so all of the reactions that we're going to look at today will involve that mechanism, but there's going to be just a few differences, and I just want to point out what those differences will be. So difference number 1 is the identity and how we form the electrophile. So we're going to do nitration, we're going to do chlorination, we're going to do sulfonation, we're going to do alkylation, we're going to do acylation, and all of those things involve an electrophile, but the identity of the electrophile is different. And that means forming the electrophile is different. And so that's going to be one of the main differences in all of these mechanisms, is how we form the electrophile. And so I showed you how we form the electrophile for bromination, and I'll show you how we form the electrophile for all of the reactions. And that's something that you want to make sure that you're studying as part of the reaction mechanism. How do we form the electrophile? The other big difference is going to be the base and how we show it acting. So in other words, the other differences come at the end of the reaction. What's the main thing that stays the same? The main thing that stays the same is this sigma complex. The sigma complex that we form that's resonance stabilized, there'll be 3 versions of it in every single reaction, and they'll all essentially look the same. And so that's one of the things that we're really going to be doing over and over and over again that should kind of like eventually towards the end of the day you should have that part down. And so let's take a look at chlorination and let's see how that chlorination business works. So here's the reaction. If I were to just put it on a reaction board, it would look like this. Cl2 reacts with AlCl3 and it installs a chlorine on a benzene ring. So almost exactly analogous to the bromination mechanism. In fact, the way that we make the electrophile is exactly the same way, but instead of chlorine reacting with iron, or excuse me, with bromine reacting with iron, we're reacting chlorine with aluminum. But everything else about it is exactly the same. Everything else about it is exactly the same. This is the electrophile. And so the mechanism then starts with the formation of that sigma complex, and that starts out our resonance structures. And it finishes off similarly. The electrons in one of these bonds acts as the base, and that reforms the aromaticity. And then that forms our final product. Okay, so that's chlorination. What's the differences and what's the similarities? Well, the differences is that instead of iron tribromide, it's aluminum chloride. Instead of bromine, it's chlorine. But at the end of the day, we're forming the same type of electrophile in the same way with the same mechanistic moves. Once we've formed the electrophile, everything else in the reaction happens the same way. The double bond comes out, it attacks the electrophile, and the sigma complex forms. There's 3 versions of that, and then something comes along and acts as a base. All right, so let me just pause real quick right there and see if there's any questions about chlorination. So far we know bromination and we know chlorination. All right. The next one is sulfonation. Sulfonation involves fuming H2SO4. So it's hard to see in this example, so I'll redraw it real quick. I'm not going to draw everything. I'm just going to draw the hydrogen that gets moved. This is a little bit of a different mechanistic move. It is a proton transfer, but we don't usually show it this way. So I'll warn you, where we're showing it is we're showing the electrons on the chlorine simultaneously leaving the aluminum and doing the proton transfer. Another way to show this would be to show a lone pair here, show that go there, and then have the lone pair do the attacking. But at the end of the day, you are making HCl. So the chlorine doesn't leave in the sense that it's by itself. It's hanging around with a hydrogen and it's making acidic conditions. So it involves, so sulfonation involves fuming H2SO4. Fuming H2SO4 is concentrated sulfuric acid, and it's what's the fuming part? The fuming part means that it has SO3 gas in it. That's what's actually fuming off of the H2SO4 concentrated acid solution. So it's this plus that in the solution at the same time. SO3 itself is the electrophile. This is a powerful electrophile. And so it looks like this. Remember, sulfur can do an expanded octet, but at the same time, oxygen is more electronegative, so it's partially positively charged. So this is how we start off the reaction, and we form the sigma complex. Oops, I didn't finish the reaction over here. That's the product that we're working towards here. So here's the basic reaction. Benzene with fuming H2SO4 produces the sulfonated benzene. It's SO3H is the reagent, or is the group that is attached. So we still end up with a sigma complex. I can still show you 3 different resonance structures. This is negatively charged. 1, 2, 3. This is negatively charged. The positive charge delocalizes around the ring. Make sure I'm not doing this correct, actually. Yep, that's where I messed up. It's right here. This bond should be here. That bond should be there. Now we got it. Negatively charged. And remember, there's still a hydrogen here. Okay, so now this is one of those differences I was telling you about. What comes along and acts as the base? In this case, it's water that comes along and acts as the base. That's what's going to do the proton transfer that restores the aromaticity. Just need a little bit of room. And so that gets us this product. And as I said before, the end of the reaction is what's different sometimes. And so I still have a negative charge here that I have to deal with. Well, that's good. That's all well and good. I just made some H3O plus, so I can use that H3O plus to protonate that negatively charged oxygen. And that's how I get the final product for sulfonation. That's where we are with that one. But at the end of the day, I've still got electrophilic, nucleophilic attack, or with this being the nucleophile. So nucleophilic attack of the electrophile, formation of a sigma complex, showing the 3 different resonance structures in the sigma complex, where the electrons are all delocalized. And then showing something come along and acting as a base. to restore the aromaticity. The only difference here was the end of the reaction. I still had a negatively charged oxygen to deal with, and I can deal with that with the H3O plus that's created in that last step. So a little bit different there. So I want to pause just a beat to see if there's any questions about that. Okay, so one of the things that this reaction is good for is that if I take a sulfonated benzene and I react it with dilute H2SO4, then I get the reverse reaction. I go back to benzene. And this is called a, we're going to later, we're going to use sulfonation to install a blocking group in order to prevent a subsequent addition on the ring in a location where I want to then later install another group. So this is analogous to alcohol protection when it came to Grignard reagents, but instead it's not protecting a functional group, it's installing a functional group in a location to prevent other groups from being installed there as well. So this is why we call it a blocking group. Sulfonation is particularly good for this because it's reversible. In the forward direction, we use fuming H2SO4 that produces the sulfonated aromatic. If I use dilute H2SO4, then I go the other direction and remove the sulfate group. So that's what we're going to be using that for later on down the road, but we're not going to learn about that today. We're going to save that for the next lecture. So let me move on from there. Let me know if you have any questions. All right, so nitration. That's what's next. So nitration is taking a benzene ring, reacting it with nitric acid in the presence of sulfuric acid, and we get one of those nitro groups on there. So there's nitrobenzene. So that's the basic reaction, and again, it's going to be the exact same mechanism that we've done before. The only difference is how do we create the electrophile. So here's the Lewis structure for nitric acid. It's neutral, but I've got a negatively charged oxygen and a positively charged nitrogen. It's going to react with H2SO4. Remind you of the Lewis structure for H2SO4. It's a much stronger acid than nitric acid. If you take a look at the pKa tables back in chapter 3, you'll see then that it protonates the nitric acid itself. And then ultimately what this is going to form is this is a nitronium ion. This is our electrophile in this case. The nitronium ion is our electrophile. So now that we have an electrophile, we can take a benzene ring, extra arrow there to show my octet rule. Now I've got NO2, negative there, positive here. These double bonds are still in place. Now that's my sigma complex. What I'm hoping is that at this point, the mechanism itself is fairly straightforward. That, especially once we get to the sigma complex, you should be able to draw out all of the different versions of the sigma complex as we go. Electrons move there, electrons move there. And now the difference is, well, what's the base in this case? Now I've still got a hydrogen here. Just kind of expand this out a little bit. In this case, it's just water that comes along. And that's ultimately what forms our product. So again, the same reaction mechanism over again. Does it matter? The question is asked, does it matter which double bond attacks the nitrogen? It doesn't matter. So you can show any one of those double bonds attacking the nitrogen. It doesn't even technically matter then how you show everything faced in the next step, because remember, you could always rotate that sigma complex around to sort of get anything you wanted, and you could flip it over. And so for the ease of grading, what I suggest that you do is, once you've picked a double bond, so for instance, I picked this double bond, then I left these double bonds in the same location. Again, it didn't matter to me whether or not I put the nitro group here or there, as long as I was consistent with all of my other drawings. I decided to put the nitro group there, so I left it there in each one of those cases. And so that helped me then be consistent in where I showed the electron movement. And that just makes it easier for the grading. And the easier it is for the grading, the easier it is to establish that you understand the concept, the easier it is for you to be assigned all of the possible points with that. Does that answer your question? Cool. Again, it doesn't technically matter. Now, one of the cool things about nitro group is, now that we have that on there, we can reduce it. If I react that in the presence of iron or zinc with HCl, and then finish it off with some sodium hydroxide, I can get rid of those oxygens and reduce them to hydrogens, and now I've got aniline. And so we can actually show a total synthesis of aniline from benzene, with the first step being the nitration step, and the next two steps being the reducing steps. And I'm just going to choose zinc and HCl. And now we have aniline. Okay, so a little bit of an extra reaction at the end. So now we've got, once we have a nitro group on it, we can reduce it. Okay, we're getting close to the last bits. What we want to talk about now in the next two reactions are both Fredo-Crafts reactions. The first one is Fredo-Crafts alkylation, and the next one we'll talk about will be acylation. In alkylation, we're taking a benzene ring, we're reacting it with an alkyl halide, and this is in its basic sense, with iron trichloride, and we're installing the alkyl group on the benzene ring. Okay, this is pretty neat, but there are some limitations. And the first thing that I want to talk about is the limitation in this alkyl group. The reason why there's a limitation is that it involves the formation of a carbocation. And so let me show you what I mean by that. Let's take this R group and let's make it a chloride like that. And so you're going to find that the reaction is quite similar to what you saw before with aluminum trichloride and iron tribromide, but you get this formation. Oh, you know what? I want to make sure that I've got, I think I wrote down iron. I think it is actually aluminum. Let me just double check. Yeah, that wasn't making any sense to me. Yep, it is aluminum trichloride. So let's just erase this iron. Put an aluminum here. Okay, this makes a little bit more sense now. But it's exactly the same as it was before is where I was going with this. It reacts exactly the same way. Man, I'm setting this up all over the place here. And we get a negatively charged aluminum and a positively charged chlorine. But what happens is there's actually quite a bit of character where this actually forms a carbocation as such. Okay, here's the limitation. The limitation is that when we form the nucleophile in the Fredo-Crafts alkylation, we are forming a carbocation. And so think about what could be the problem with a carbocation that's formed as the electrophile in an electrophilic aromatic substitution reaction. Well, and the same sort of situation occurs in these reactions as it did in in organic chemistry 1. And that's that you have to worry about rearrangements that can happen. Now, in this particular case, I'm forming a secondary carbocation. There isn't a more favorable carbocation that can form, and even the other secondary position is it leads to the exact same intermediate, the same carbocation, so we won't get any sort of weird behavior going on. And so at the end of the day, I'm going to show you then the rest of the mechanism for this particular intermediate. Everything else starts off exactly the same way. Connected in that second position now. I've formed a sigma complex. The sigma complex is resonance stabilized. There's still a hydrogen there. Now I have to think about what's the base that comes along to do this reaction. It's the same thing as before. AlCl4 is still around, serving as the counter ion for the sigma complex. So I still show this slightly unusual proton transfer move to form our final product. So this is alkylation. This is alkylation. It involves the same mechanism, but again, what's different is the formation of the electrophile. One of the things that we have to consider in the formation of this electrophile is the fact that it is a carbocation and then would be subject to rearrangement. So if you were to react something like this, with something like this, then the product you would get would be this. And that's because when I'm forming the electrophile, I'm ultimately forming a primary carbocation. And then this carbocation will undergo a hydride shift to form a secondary carbocation counterbalanced with AlCl4. And so this is why I get this product rather than the primary product that I'm looking for. And so you have to be careful when using alkylation when you're thinking about synthesis, because you're going to have to very carefully pick the reagent in order to avoid problems with carbocation rearrangement. So we showed you some things that wouldn't be subject to rearrangement. These would all form the more stable and symmetrical cations. Of course, a methyl chloride wouldn't have to worry about any sort of rearrangement. But once you start to get a little bit more complicated chlorides, then instead of forming carbocations and doing alkylations at that point, you'll start to do some rearrangements, and they'll attach in different locations. So think about rearrangements as a possibility. Now, there's a couple of other considerations that need to be made as well. Now, there's one thing to point out is that in real life, electron with a donating group, like an alkyl group, is actually an activating group when it comes to subsequent alkylations or subsequent. Can I explain that more slowly? The hydride shift. Well, this is the reaction, or this is the intermediate that we formed. This aluminum tetrachloride that's got a negative charge in the carbocation. But this is a primary carbocation. And so if these hydrogens are allowed to shift to this position, then the positive charge moves here. I'm still counterbalanced with AlCl4, but now the entire alkylation process happens at that location. Is that what you were looking for? Cool. So again, the alkyl group attached to the benzene ring is an activating group. So it does the next alkylation faster. So in real life, polyalkylation is difficult to avoid. Luckily for you in this class, we will assume monoalkylation for our chemical synthesis reactions, for any time we're doing synthesis. So the note is that in real life, if you were to walk into the lab, it would be difficult to prevent additional alkylation from happening. In this class, I will assume that you can do reactions with a single alkylation. Another real life problem that we can't avoid, and we won't be avoiding it in this class, is that nitro groups are electron donating, or excuse me, electron withdrawing. And not only are they electron withdrawing, they're very electron withdrawing. And electron withdrawing groups are very deactivating. And the nitro group is the most deactivating. We're going to get a lot further into activation and deactivation later. But the bottom line is that if you tried to do alkylation at this point, we see no reaction. So it means that it's deactivating for further EAS reactions, for further electrophilic aromatic substitution reactions. So while I'm okay with allowing you to use this reaction to form a possible product that looks like this, even though we know in real life this is really what will be the major product, what I won't let you do is do an alkylation with something that has a nitro group on it, because it'll be too deactivated at that point. And so again, when I say activating and deactivating, I mean towards additional electrophilic aromatic substitution reactions. If it's activating, then that means the next one that happens faster. If it's deactivating, then that means the next one that happens slower. What we're going to say is that in the case of nitro groups specifically, they're too deactivating. They deactivate to a too strong of an extent to do any other electrophilic aromatic substitution reactions afterwards, particularly alkylation and acylation. All right, so I want to pause a beat real quick and make sure that I don't have any questions there. So the question is asked, will further electrophilic aromatic substitution reactions always install in the para position? And the answer to that question is no. And that's really the next part of this chapter. It's talking about where those reactions direct the next substituents. And what we're going to have to do before we start to talk about that is we're going to have to examine all of the possibilities, which ultimately is going to mean we're going to draw resonance structures until our eyes bleed resonance structures. And then we'll look at those resonance structures and we'll decide which ones of them are more stable and which ones of them are less stable. And that'll help us decide which way these things will direct, whether they will direct ortho and para or whether they'll direct meta. And we'll have a whole conversation about that, but we're going to save that for next time. Yeah, and so there's one, right now what we're doing is we're just learning the reactions. So we're pretending that there's no other substituents on there. We're just talking about some very small, important factors about if there were later on. We're not going to do it this way, but right now we haven't even gotten into that bit. So the last thing we want to talk about then is Fredo Craft's acylation. And an acyl group can be installed on a benzene ring in a very similar way. With an acyl chloride in the presence of AlCl3. And in this fashion. This is an acyl group. Okay, so again, it's the same mechanism as before. We're just going to have to learn a little bit different way to form a electrophile. It starts off with an acyl group, and it starts off with AlCl3. And I'm sure you're not surprised, but the chlorine attacks the aluminum, and it forms a four-membered tetrahedral intermediate with 4 bonds. It means it has a negative charge, and there's a positive charge there. What happens, though, is, like before, the AlCl4 will go off on its own and will form this cationic species. This is an acyl ion. And what's interesting about this ion is that it is resonance stabilized. One of the lone pairs on the oxygen can make a triple bond with the carbon. And we can show the positive charge delocalizing into the oxygen. And so this is just yet another new way to make an electrophile. And so we've learned several different ways to make electrophiles. This is yet another new way to do that. But once we've made the electrophile, then all of the reaction mechanism is exactly the same. Now, it doesn't matter which one of these I show. I'm going to show that one. Still have a sigma complex. I'm still going to show the 3 different resonance structures in the sigma complex. And then I'm still going to show something coming along as a base. And it's still the same thing as it has been for these other reactions that involve AlCl3. I'm going to show this guy here. I'm going to show this guy moving over here. And then I'm going to show this guy reforming the aromaticity. And this gets us to our final product. I'm going to be consistent here. All right, that's our final product. Now, the cool thing about this final product now, one last reaction, is that it can help me avoid all of the problems with using alkylation to form carbon chains on benzene rings. It's susceptible to reduction as well. The acyl group itself, the acyl ion, will not rearrange. So even if the R group is quite a long chain of carbons, I can get a long straight chain of carbons without any branching attached to a benzene ring by doing acylation first and then reducing the ACL group with zinc, mercury, HCl, and heat. That's what'll get me my straight chain. So even if this R group is a longer chain of carbons without any branching, I can successfully install it with this series of reactions. This would be a challenge to do with alkylation, but it's pretty straightforward to do with acylation. And so that's going to be it for now, because the next thing that we're going to talk about is going to be taking a look at what happens with these groups when I want to do another electrophilic aromatic substitution reaction after there's already a group on there. And so then you'll see if there's a group on there, there's a lot of different places where the next group could install. And there's only going to be certain ones of those places that will be the correct answer. And so that's called the directing effects. And we sort of talked about it a little bit already, but that's where we're going next.